Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to talk about an add-on that we're going to be implementing for our A3C algorithm. It's called the long short-term memory, or the LSTM for short. So let's have a look at what we have so far, and then we'll discuss why we need the LSTM and what an LSTM is. So far we've discussed the A3C algorithm. We've talked about all three letter A's in the A3C, and of course we've seen that it's actually a bit more complex, much more complex than what we have on this image. We actually have three or more, multiple agents going through the environment, and they're communicating between each other and so on. But for simplicity's sake, for today's tutorial, we're going to just illustrate everything with this one agent. At the end we have this actor part, the critic part. So basically once we have a state, that state of this image goes through a convolutional layer, then it goes through a pooling layer, goes through a flattening layer, and at this point we have values or numbers which are then propagated through the network, and they go into the hidden layers, and then as the output we get the policy or the actor part, and they get the value of the state, or we get the critic part. And what we're going to do today is we're going to talk about this hidden part. So in the hidden layers, we can actually take it to the next level, and we can add a modification. And we've already seen that multiple modifications exist for the A3C algorithm. We've seen one of them. We've seen that in some cases you can have this main part of the network which is individual to every agent, or you can have this main part of the network which is shared. And that's what we saw, that in our previous intuition tutorials we had a shared part of the network. This network was shared between the agents, and as Adlan will tell you more in the practical tutorials, that really helps with the challenge of breakout. And there are lots and lots of other ways you can modify the A3C algorithm, lots of other additions that can be implemented. And one of them we're going to discuss, because we're actually going to have it in the practical side of tutorials. Here, before your hidden layers, which you can add, is an LSTM layer, a neural network layer, which allows your A3C algorithm, which allows your algorithm to have memory, which allows your algorithm to remember what happened before. And we'll talk about LSTM just now in more detail, but basically you can add an extra layer here, which is the LSTM layer, and enhance your algorithm with some additional memory, with another feature. And what you'll actually see in the practical tutorials is that we didn't even need any hidden layers after the LSTM layer. So you'll see that in Adlan's implementation, he's got the flattening layer. Right away after that, he's got the LSTM layer. So basically this box represents the LSTM layer. And then after that, right away, you've got the output. So you didn't even need any other hidden layers after that, simply because that's how much power the LSTM layer adds to the algorithm. And again, the algorithm, or the architecture of your neural network, it's a very individual thing. It's a personal preference. It's a very creative thing. So you might want to have two LSTM layers. You might have an LSTM layer, and then several, like 5 hidden layers after the LSTM. That's totally up to you and for you to experiment and explore. But this is what we came up with in the practical tutorials. So you'll see that we have a flattened layer, and after that, we've got an LSTM layer, and then the output. So now that we've talked about the LSTM layer so much, what is this LSTM layer? Well, the LSTM layer adds memory, gives a feature, like allows the neural network to have memory about what happened in the previous iterations. And it is often symbolized or shown with a symbol which looks like this. This is us just getting started into it, and I'm just putting here, I know it looks very crooked, but I'm putting it here so you can see when we further discuss this image, you can see what's going on. So the output of this layer goes into here, and that is our so this is a whole layer going in here. So it's a vector of values. X is a vector of values, goes into the LSTM, which we'll just discuss just now. And then as an output, you get another vector, which is, the concatenation of these two, or somehow it ties in with network. In our case, as an output, you get this and you get this. So let's have a look at this in more detail. So we're just going to focus on this part. In fact, we're going to, as you probably noticed by the letters being on this side, we're going to turn it to the side. So like that. And this whole jumble around was just to reiterate the fact that even though it looks like this, what is actually happening is a layer of values, a whole vector of values is going in here. Something is happening, which we'll discuss just now, and then a whole vector of values is going on here. So this is the layer. It's not just one element of this is the layer itself. So let's go back again, just to reiterate. Layer goes into this layer, something happens, layer comes out. So that's the LSTM. It's just on its side. So it's just easier to discuss this way. And that's the common representation. All right, now that we agree why this image was on its side and how we're going to proceed with this, let's start digging into this LSTM situation a bit more. So what happens inside the LSTM layer? So this is what it looks like. And of course, looks very complex, and we're definitely not going to go through all of this right now, simply because there's quite a lot to discuss. These are point-wise operations, these are layer-wise operations, and there's just a lot going on, or a lot of intricate details which we're not going to go into, because otherwise it would blow out this course. And this is not, the purpose is not to talk about LSTMs here, which is going to utilize each LSTMs. And if you'd like to learn more about LSTMs, you can either go to over here, Christopher Ola's blog. He's got a good description of LSTMs, or we also talk about LSTMs in our Deep Learning A to Z course. You can check it out there. We've got a whole section on recurrent neural networks and LSTMs as well. So basically, this is the internal part of the LSTM, and what happens is, like, the layer goes in. So we're going to talk about this on an intuitive level, on a very basic intuitive level, just what is going to be enough for us to understand what happens, why there's memory, and so that you can also better understand what Adlan is talking about when he's implementing this. So a layer goes in, all of this, something basically goes on here, a layer goes out. What we need to actually see is that these parts, there's actually additional inputs into this layer. So remember this, usually you have like an input from a previous layer, then this layer, and then you have an output. If you think of that image we had previously, the normal network, which is not on its side, which is like from left to right, not from bottom to top. But with an LSTM, you actually have more inputs. So I know it's getting even more complex. But these things, at least we can understand them. So this is your memory cell. This is the key, and this is what you'll hear Adlan talk about. So the memory cell is something that is saved in the LSTM. So these inputs and these outputs, they're actually, here what you're looking at is the time axis. So this is unraveled in time. So in one specific iteration, this happens. But then this value is taken from the past, and this value is passed into these values are taken from the past, and these values are passed on to the future. And how they pass? Well, through the way the LSTM works. So without worrying about too much what's going on here, all we need to understand is that the layer goes in, and here we already have a value which came from the past, which is stored inside the LSTM, inside the long short-term memory. We've got this memory cell, and whatever value was here before, it just stays here. As you can see, it just goes through. It flows through freely, except for these point-wise operations where it can be either closed off or something can be added to it. But regardless of that, it's just some value that flows through freely. So it's basically, it's passed on to the next point in time, So you can just think of it as like some memory that, like a flash drive or something like that this cell has. And so it just remembers the previous value that was in here. And then it can use that to either add to it or read from that value and so on. And this value is the hidden state. So hence the H. And the hidden state is basically another value that comes from the past and then is used inside the LSTM. And as you can see at the end, after all of this happens, what you get is you get a layer that comes out, and so you get this value that comes out, and it is the same value that's passed forward. So basically, the LSTM remembers two things. There's a constant value that is just like stays in the LSTM that can be changed. Like there's a flash drive for like a constant value, so the memory cell, and so you have the luxury of storing something in that space, in that memory, and it'll be passed on to the future. So whenever in the next iteration, so like the algorithm was in an environment, it saw something, did something, and so on, and then in the LSTM you can store a certain value, and then it will remember this value even when it's in the next state. And also the other value that it will remember its previous output. It automatically will remember its previous output. So the output goes here and goes here. So that's basically the very, very, very high level of what happens in an LSTM. Once again, if you'd like more details, there's lots of resources where you can find. And at this stage, we just don't need to go into that much detail on all of these things. We just need to understand, what a memory cell is, what a memory cell is, what a hidden state is, and how they facilitate memory for the LSTM. And the question is, so now that we kind of have a general overview of all of this, to reinforce or to solidify this knowledge, or kind of like give a reason for this knowledge, let's ask the question, why do we need memory? Why do we need memory in our A3C or other algorithms? Well, let's look at our example, the challenge that we're taking on in this section. So the challenge is breakout. And what happens in breakout? Well, in breakout, you've got this environment, these little blocks that you need to destroy with this little ball, and you need to make sure that this is your kind of like racket or platform that's moving around, and it must, wherever the ball is flying, it must catch the ball, and it'll bounce off the platform and go back and hit. It'll bounce off the walls as well and go back, hit a block, and come back. And so that's the essence of what you need to accomplish. But now let's look at this ball. Like, imagine you're an A3C algorithm, or an agent inside one of those agents inside A3C. You see this picture. What do you extract from here? What would your actions be here from here? So you can see the ball is flying, right? So, well, it's flying, right? So it's going somewhere, and maybe it's flying towards you, right? Could you make this conclusion? Could you like anticipate that it's coming towards you? You probably could, and maybe you're in the right spot to catch the ball. But what if the ball is actually not flying that way? What if it's flying that way? The thing is, you cannot tell from this one image which way it's flying, because you don't know where it was in the previous moment of time. So if it was here, then it's flying this way. So if you knew the previous moment in time, if you knew that it was here, then now you know here, as a human, you just draw a line from these two and you'd be like, oh, cool, so it's going this way. But if you knew it was here, you draw a line from these two and it's going this way. Moreover, look at this. It could have actually been somewhere like over here. Maybe it's going up. Maybe it's actually going that way. So maybe it was here and now it's going upward. So just from that one image is very hard. It's actually impossible. It's just like geometrically impossible to tell which way the ball is flying. And so that's why the LSTM, the memory, actually really, really helps algorithm. Without the memory, you can still do a good job. It could probably like guess or find other ways of understanding where to go. But with the LSTM, with just even that one memory, so if we go back, even with that one value, well, that was kind of like the output of the previous value, or maybe you can store it here, or based on this value, like based on the information that it gets from the previous point in time. So let's say from what happened here. So that's where your ball was before. So you can pass on information about the environment from the previous point in time through here. And then now you have it. Now you don't not only have your information from the image. If we go back even further, you'll remember that information from the image, well, this is Doom, but we're actually working with Breakout. Information from the image came here, turned into these flattened values. And so that's information from the image coming into the LSTM. And now all of a sudden, as you remember, coming from not from somewhere, but from the previous point in time. So that's why you can't actually demonstrate it's coming from the top or from the bottom, from the left, right. It just stays in the LSTM layer. You have that information just through the architecture of the LSTM. You have the information about what happened previously. And so we go back. That information here helps you now make a decision on what to do, helps the algorithm make a decision. And now all of a sudden it knows that, okay, so the ball is actually flying in either direction. Let's say it's flying in this direction or in this direction, so I'm in the right place. So I should stick around here. The ball is coming in my direction. Or if it realizes the ball is flying there, it should start moving to the left, because if it waits a bit longer, it'll be too late and it'll miss the ball. So basically, that's how the LSTM layer really helps in this algorithm, and that's exactly what we will see when you're doing the practical tutorials with Adlan. So there we go. That's how LSTMs work. And just one additional note. As we mentioned at the start, LSTMs are not 100% necessary. They're not they're not completely attached to the A3C algorithm. You might want to have them in the A3C algorithm. You might not want to have them depending on the situation, depending on the architecture you choose. There are lots of additions, and We've already discussed the addition or the modification where the neural network is shared between actors or is not shared between the agents or not. Now the LSTM. There's another one that you will see in the practical tutorials where we add entropy, which is calculated through a policy loss, and Adlan will walk you through that. So basically, there's lots of different modifications that can happen in an A3C algorithm. Just remember that it depends on what you want to achieve, and it's also something that we'd encourage you to explore if you're going to be implementing lots of these and trying out different algorithms. We've already discussed a couple, and maybe you can find some additional modifications that might be of interest to you. Or maybe when you're watching these tutorials, maybe by then more modifications have come out, which are very interesting. So definitely that's something that you could look into, and that could further enhance your knowledge of artificial intelligence and how to create these algorithms. And on that note, I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI.